Hey everyone, and welcome to the Deep Dive, where we take a closer look at complex topics. Today we're diving into the world of quantum gradient descent, with an essay by Jorgo Schneeppert as our guide. Have you heard of this before?
Oh yeah, it's a fascinating area where quantum computing meets AI. Basically, it's about finding the best solution to a problem, but with a quantum twist.
Okay, that sounds pretty cool, but I'm going to need you to break that down for me a bit more. What exactly makes it quantum?
Well, imagine you're trying to find the lowest point in a valley. That's kind of like what classical gradient descent does. It tweaks things bit by bit until it finds the best solution, like the bottom of that valley.
I'm following so far.
Now, in the quantum world, we're not dealing with a physical valley, but a mathematical function. And our tools are qubits, which can be in multiple states at once. It's like they can explore many paths simultaneously.
So it's like having a team of explorers instead of just one, and they're all checking out different routes at the same time. That sounds way more efficient.
Exactly. That's the power of quantum parallelism. It allows QGD to explore many potential solutions concurrently, potentially leading to exponential speedups.
Okay, I'm starting to see the appeal. But how do we actually guide this quantum search? Do these qubits just wander around randomly?
Not exactly. That's where those quantum building blocks come in. We have quantum gates, which are like instructions that manipulate the qubits, and oracles, which provide information about the problem we're trying to solve.
So the oracles are like the map and compass for our quantum explorers, guiding them towards the best solution.
Precisely. They're crucial for steering QGD in the right direction. And then there's phase estimation, which is like a special technique that helps us figure out the direction and magnitude of the gradient.
It's like having a super-powered compass that tells you exactly which way to move to get closer to your destination.
Exactly. It's all about efficiently navigating this complex quantum landscape.
This is fascinating stuff. But let's get to the practical side. Where does QGD really shine? Schneeppert mentioned some pretty exciting applications, right?
Oh, absolutely. Imagine designing new drugs or materials at the molecular level with incredible precision. QGD could revolutionize fields like medicine and material science.
Wow, that's huge. We're talking about potentially finding cures for diseases or creating entirely new materials with incredible properties.
Exactly. And it's not just limited to those fields. Think about finance, where complex models could be tackled with ease using QGD. Or AI, where QGD could supercharge the training of deep learning models.
So Wall Street and Silicon Valley might be getting a quantum upgrade. It seems like QGD has the potential to impact so many different areas.
The possibilities are truly mind-boggling. But of course, there are limitations and challenges too.
Yeah, I was just thinking about that. Building a quantum computer sounds incredibly complex, and we've barely scratched the surface of understanding quantum mechanics.
Right. Building and controlling these delicate quantum systems is a huge hurdle. And designing those oracles, translating our problems into a language that the quantum computer can understand, is a challenge in itself.
It's like we're still learning the alphabet of this new quantum language. But despite these challenges, the progress being made in the field is impressive.
Oh, absolutely. It feels like we're on the verge of a new era, a hybrid quantum AI era where QGD could play a pivotal role.
It's exciting to think about the possibilities. But for now, let's take a little break. We'll come back and explore what this quantum future might look like in the next part of our deep dive. Stay with us. And we're back, ready to continue our deep dive into quantum gradient descent. Before the break, we were talking about some of the mind-blowing possibilities of QGD and also some of the, pretty big hurdles we still need to overcome, like actually building those quantum computers, for one thing.
Right. It's definitely still early days.
So is it fair to say that QGD is not like a silver bullet that can solve any problem we throw at it?
I'd say that's a good way to put it. While QGD holds immense potential, it's particularly effective for specific types of problems, those with structures that quantum algorithms can exploit really well. It's not a magic wand that can solve every optimization challenge out there.
So some problems are just better suited for QGD than others.
Exactly. And even for those well-suited problems, the quantum advantage might vary. Sometimes it might offer a modest speedup compared to classical methods, but in other cases, it could be truly exponential.
So we need to be strategic about choosing the right battles for QGD.
Absolutely. And there's another challenge that comes up even when we find that perfect problem for QGD, something we haven't really touched on yet, interpreting the results.
Oh, right. Because quantum mechanics is, pretty weird.
Yeah. It operates in ways that often defy our everyday intuition, so understanding what those quantum solutions mean in a practical sense can be quite tricky.
It's like getting an answer in a language you don't fully understand. You might have the solution, but you're not sure what to do with it.
That's a good analogy. And it brings up another important point, validation. How do we know that the solution QGD spits out is actually the best one? In classical computing, we can often verify results through simulations or even direct observations, but the quantum realm is a whole different beast.
So we need new methods to double-check those quantum insights to make sure they're actually leading us in the right direction.
Precisely. We need to make sure we're not just getting random quanting noise. It's all part of the ongoing exploration and development of this really exciting field.
It sounds like a pretty wild ride. So much potential, but also so much to learn and figure out.
Definitely. And that's the beauty of scientific progress, right? Constantly pushing the boundaries, questioning assumptions, and refining our understanding. It's a journey, not a destination.
Well said. Okay, so we've covered quite a bit of ground today, from the very basics of quantum mechanics, which are, let's be honest, mind-bending, to the exciting possibilities and challenges of quantum gradient descent. But before we wrap things up, maybe we should take a moment to reflect on what we've learned so far. Anything that particularly stood out to you?
Well, for me, it's the sheer potential of QGD to revolutionize various fields. I mean, the idea that we can harness these incredibly strange and powerful quantum phenomena to solve real-world problems is just mind-blowing.
I agree. And for all the challenges we've talked about, it's really encouraging to see how rapidly quantum computing is advancing. It feels like we're on the cusp of some major breakthroughs.
Absolutely. The pace of innovation is truly remarkable. As the technology keeps developing, we can expect even more amazing applications of QGD to pop up. Who knows what we'll be able to achieve?
This has been an incredible journey. Now, before we conclude our deep dive into quantum gradient descent with Jurgo Schneeplatt as our guide, let's turn to a final thought-provoking question, something to leave our listeners pondering.
A question that really gets at the heart of what this technology could mean for our future.
Stay tuned for the final part of our deep dive. Welcome back to the deep dive. We've been exploring quantum gradient descent, guided by Jurgo Schneeplatt's insights. It's amazing to think how QGD could completely change how we solve complex problems.
It really is. We've talked about everything from the pretty bizarre world of quantum mechanics to how QGD might revolutionize fields like, medicine, finance, even AI.
Exactly. And now, as we wrap up our deep dive, we want to leave you with something to think about, something that goes beyond just the technical stuff.
Yeah, a question that gets to the heart of what this could all mean for us, for the future.
So just imagine a world where QGD is no longer just a theory, but an actual tool we can use.
A powerful tool.
Right, and we're using it not just for, designing new drugs or optimizing financial models, but to tackle even bigger problems, challenges we haven't even thought of yet.
Exactly. Problems that seem impossible to solve right now.
What if QGD could help us finally understand, really understand the complexities of climate change?
And maybe even help us develop real solutions for a sustainable future.
Or what if it unlocks new forms of clean energy, something we can't even imagine right now?
Yeah, pushing the boundaries of what's possible.
So in a world where QGD helps us solve some of humanity's biggest challenges, what new questions will we face? What incredible new possibilities will emerge? It's pretty mind-blowing to think about.
It really is.
We hope our deep dive into quantum gradient descent, inspired by Jurgo Schneeplatt's essay, has, sparked your curiosity about this amazing field.
If you want to explore this even further, I definitely recommend reading the original essay.
It's a really fascinating read, and it'll give you a much deeper appreciation for, the sheer potential of this incredible technology.
Thanks for joining us on this deep dive.
Until next time, keep exploring, keep asking questions, and keep diving deep.